Hello, I would like to thank you for attending today's presentation. As a quick outline of the presentation that we're providing today, quickly we'll just cover some general concepts of amino acid nutrition to discuss ingredient volatility and nutrient variation, and to discuss the order of limitation from the standpoint of ingredient profile and how that will influence the way we approach trying to reduce crude protein in diets. Then we'll talk a little bit about the benefits of reducing crude protein and the potential impacts that it could have on animal performance, animal welfare, and gastrointestinal health, as well as the environment for the animal. And then we'll wrap up the presentation discussing some recent advances in branched chain amino acid nutrition and balance in poultry, follow up what our colleagues on the swine side have done, really looking at the branched chain concentrations within the feedstuffs, the metabolism, and the impacts that elevated levels of dietary leucine can have on valine and isoleucine from the standpoint of optimization of feed conversion and breast meat yield and carcass yield. So these are two schematics showing corn and soybean meal pricing for the last 5 years. Obviously, those of us, everybody that's attending this seminar realizes that over the last year to 18 months, we have seen some extreme volatility regarding pricing of both corn and soybean meal. These areas, as you can see, dramatic increases in the price of both commodities. Obviously, this will have a dramatic impact on the cost production of raising poultry, swine, or any other animal. Therefore, understanding and utilizing technologies that are available to us can be beneficial to try to control diet costs. I'm sure the vast majority of the attendees have seen this schematic or diagram, the barrel theory. Here in an unbalanced barrel, where we do not have any added lysine in this diet, lysine being the first limiting amino acid in particular for this example, we see excesses of the additional essential amino acids, threonine, isoleucine, valine, tryptophan, so on and so forth. As we add dietary L-lysine, feed-grade amino acid, we increase the amount of lysine present in the diet. We're able to capitalize on a performance benefit associated with increasing the amino acid density of the diet. At the same time, where we're capitalizing on performance, we're also utilizing a much higher percentage of the other essential amino acids that are present in the diet, getting much closer to or reducing the amount of amino acids that we're overfeeding. And so if you think about the current situation in the animal ag industry over the last couple of years, we've had the commercialization of valine, isoleucine, arginine, and we've had tryptophan available for several years. But as we continue to improve efficiencies, all of these products they start to become economically feasible from the standpoint of inclusion in animal feeds. Therefore, we can meet the dietary requirement of these animals much closer to what is actually in the feed, eliminating a lot of the excess nutrients. Obviously, understanding the order of limitation from the standpoint of the animal that you're feeding and the ingredient profile that you're utilizing is extremely important. For the most part, when you're talking about poultry, methionine is always your first limiting. And then regardless of ingredient profile, lysine and threonine typically follow to be 2 and 3. Whether you're using, corn and soy, high levels of animal protein and a variety of different ingredients, the actual 4th and 5th limiting amino acid may vary or may change depending on the ingredient profile and depending on the amino acid ratios that you're utilizing. So understanding that order of limitation is extremely important, because as you add additional amino acids into the diet, we need to have a very good understanding of what the requirements and the nutrient specifications of the additional lower amino acids are, so that we don't create a situation where we potentially or have a deficiency due to having a lower nutrient spec than necessary. So why should we reduce crude protein? First, environmental impact, the reduction of nutrient excretion can be a positive for the impact on the environment. Combine that nutrient excretion with reduction in water intake. We'll have situations within the house where we're improving the environment from the standpoint of allowing for better gastrointestinal health, improved animal welfare through the reduction of nutritive factors in soybean meal, but other ingredients as well, lower digestible ingredients, bypass protein into the gastrointestinal tract. High levels of nutrient excretion combined with high levels of moisture can lead to paw lesions. So we could have some reductions in paw quality and then gastrointestinal health. So reducing crude protein can have benefits on all of these different aspects. Additionally, we're improving sustainability, less nutrient input necessary to produce the product that we're producing. Reduction in water intake due to an adjustment in the electrolyte balance of the diet. Potassium concentration, soy milk, pretty high. So if we reduce the amount of soy meal, reduce the amount of potassium, we should observe a reduction in water intake. And then you also can expect to see an enhancement in performance. Obviously, you're going to improve the overall digestibility of the diet as we reduce protein, we reduce the amount of excess nutrients that are in the feed. But then there are going to be some ancillary benefits associated with utilizing additional feed-grade amino acids, such as pellet quality. We'll get into that here in just a minute. So here's a graph that depicts the impact of diet as we start to begin to reduce dietary crude protein. On the left, we see a progression curve showing the changes in protein ingredients in the feeds as our dietary crude protein is reduced. On the right, we see a correlating regression curve showing the impact of energy ingredients in feeds as we reduce dietary crude protein. What we see here is about a 3% difference for every 10 grams per kilogram reduction in dietary crude protein. We can expect a 3% change, a reduction in protein ingredients and a 3% increase in energy ingredients. To follow up on that, here you can see the impact that amino acid supplementation will have on soy meal inclusion level in a starter or a poultry starter diet. The first bar we have with no amino acids. So we formulate a diet with no amino acids. This diet contains 35% protein and 71% soy meal. As we add in methionine, we see a dramatic drop in the amount of soy meal necessary to meet the nutrient requirements of the animal, as well as a dramatic drop in the amount of crude protein that's present in that diet. Then as we add lysine, threonine, and now valine, which is commonly used in a variety of diets across the globe, we can see that we can reduce the amount of soy meal used in the diet from 71% all the way down to 36% in the corn soy-based diet. And the amount of crude protein that's in that diet drops from 35% to 21.8%. We mentioned pellet quality earlier. This is two pictures of a field trial that we conducted with a customer in the U.S. Recently. And they were running a diet that had a crude protein minimum. They were utilizing 3 amino acids. Through evaluation of their diet and some recommendations, we ran a study where we removed the crude protein minimum. We added in a 4th amino acid to allow for a reduction in crude protein. And these are just pictures of the diets of the pellets that were obtained from the feed mill. And you can see a visual difference in the pellet quality of these two diets. This is a study that we conducted in conjunction with Kansas State University and presented at the International Poultry Scientific Forum a couple of years ago, where we basically followed up on that field study. We ran a formulated diet, corn soy based. with and without the presence or the availability of L-valine in the diet. Our control diet contained methionine, lysine, and threonine. As you can see here, we have 54% corn, we have 39% soybean meal. We allow the ability of L-valine to come into the diet. We see an inclusion rate of 0.6 per pound or per ton, 0.6 pound per ton of feed, which allowed for a reduction in soybean meal of 2%. And as we just mentioned earlier with the graph, we would expect that 2% to show up in cereal grains, which we do see a 2% increase in the amount of corn. The additional energy from that corn reduces the amount of choice white grease that is necessary to meet the energy requirement of these birds. So we see a 0.4% reduction in supplemental fat inclusion. In this experiment, all supplemental fat was added in the mixer. So this is a reduction in mixer added fat by 0.4%. We also see that the reduction the inclusion of L-valine allowed for a reduction in dietary cost of $1.63 per ton. If you look to the graph at the right, the blue bar being the control, the red bar being the control with the addition of L-valine, we could see a significant reduction in the amount of fines that was present in the feed. And then we used two different methods, a modified tumble box method and a Holman 100 method. In the modified tumble box method, we can see we increased the PDI of the diet from about 38% up to 48%, 45%, 48 to 49%. And on the Holman, we increased it from 52 up to 68%. So significant dramatic increases in pellet quality. McKinney and Teeter back in 2004 published a paper demonstrating they used metabolic chambers and quantified the actual caloric value of pelleted versus non-pelleted feed, or the caloric value of diets ranging in the percentage of pellets that they had. And here, if you utilize this curve here, that allows for you to determine the dietary caloric value. If you use the previous example that we just saw with Kansas State, with about a 20% improvement in pellet quality from 50 to 70% with the Holman 100, that represents a caloric value of 43 kcals per kilogram. And in the US, we would expect that to be about 1.5 points improvement in feed conversion ratio, just through the adjustments in ingredient profile attributed to the inclusion of L-valine in the diet. Here's a study that was published in 2019, and we can see that we have 1% reductions in crude protein in both the starter and the grower and the finisher phase, 1%, 2%, and 3% reductions compared to the control. The concern that some producers have had as they implement, reduced crude protein diets in their production systems, are we going to lose performance? The argument is, and the fact is that typically you don't have to really worry about losing performance. You typically gain performance, partly through improvements in pellet quality, improvements in digestibility, and that's exactly what these authors published here. Body weight gain remained the same. However, you can see if you look down at the middle graph, you can see feed conversion ratio is actually significantly improved at the 2 and the 3% level compared to the control. So as we reduce dietary crude protein by 2 and 3%, we see improvements in feed conversion ratio, as well as the European production efficiency factor. In addition, we see footpad scores are improving. So we have improved efficiency, we have less production or less excretion of nutrients into the litter, the environment, and improvements in pulse scores. This was a study that was conducted in the U.S. back in published in 2021 with CJ ANH with the University of Arkansas and Dr. Sam Rocho's lab, where we actually formulated a diet similar to the previous study that we mentioned. We took a little bit of a different approach, and we allowed for a control feed to have methionine, lysine, threonine. And the treatment diet actually contained L-valine and L-Isoleucine to allow for a crude protein reduction of approximately 2% between the control and the treatment diet. This study was for 48 days, and two of the interesting observations that we observed was that the birds consumed slightly more feed, so we had a little bit of an increase in feed intake. Feed efficiency was equivalent between the two treatments. However, the slight increase in feed intake and the slight improvement, not statistical, but numerical improvement in feed efficiency allowed us for increased breast meat yield. We saw a 0.4% increase in breast meat yield compared to the control feed. Additionally, we saw significant reductions in litter nitrogen, as you would expect. So when we reduce crude protein, we expect that, or a rules of thumb, excuse me, a reduction of 1% in crude protein, we would expect to observe a reduction in nitrogen concentration of about 10% and a reduction in the use of water by about 3%. So each reduction, and in addition, each reduction of 1% in crude protein should represent about a 10% reduction in the amount of soy meal used in the diet. So if we're using 30% soy meal, reduce our crude protein by 1%, we would expect a 3% reduction in the amount of soy meal that was used in that feed. The graph on the left is a regression curve from a different study showing that the reduction, we're regressing the reduction of crude protein to the difference or the change in nitrogen excretion. And these authors reported an 8% reduction in nitrogen excretion for every 1% reduction in crude protein intake. And that reduction in nitrogen is going to be the basis for the improvements in litter quality and foot pad dermatitis improvements as well, and welfare improvements as well. This was a study published in the European Union looking at the impact of crude protein on foot pad dermatitis. They actually formulated two diets, a high crude protein diet and a low crude protein diet. Differences in these diets, obviously, when you have higher crude protein, you have a higher electrolyte balance. And so as they fed these turkeys, they placed them on new litter, and by 28 days, so within 4 weeks, they already saw a difference in foot pad quality or foot pad dermatitis score, with the lower crude protein diets having improved foot pad quality on day 28, excuse me, 56, as well as 84. So, and that continued on through 20 weeks of age. So reducing dietary crude protein, the combinations and the removal of anti-nutrient properties, the reduction of nitrogen excretion, the reduction of water intake, the improvement in litter quality, reduction in litter moisture, all of this has a beneficial effect on the bird. Here, again, published in the Journal of Applied Poultry Research, again, you can see the impact of reducing dietary crude protein on the impact of foot pad dermatitis and the scores. So this is as opposed to an average score, shows you the, excuse me, the profile. So we're on our control diet, we have 25% of the birds showing no lesions. However, as we decrease that crude protein down to 18%, 71% of the birds were showing evidence of no foot pad lesions. So you see the shift from ones and twos down to zeros as we see the reduction in crude protein take place. This was a study published by Ospino Rosas, and kind of generates and kind of sums everything up into one study. It wasn't statistically significant, but what they did was they formulated a diet, control diet, and then utilized a 3% reduction in crude protein, and then the addition of amino acids to make up for that reduction. So they balanced amino acids based on the control diet, but still achieved a 3% reduction in crude protein. They observed a 2-point improvement in feed conversion ratio, not statistically significant, but they did see large statistical separation in litter nitrogen, ammonia emissions, and litter pH. Again, establishing the benefits on environment and welfare and food quality observed with reductions in crude protein. Excuse me. This schematic is just a presentation and to kind of walk you through the protein flow in the small intestine. So protein generated from feed moves into the duodenum. You'll have some amino acid uptake by the microbiota, and then you'll have amino acid that's uptaken by the host. So that's digested. Then you're going to, on the back end, you will have microbial protein that is secreted, resistant feed protein that is present, that's undigested protein from the feed, and then you'll have host synthesized endogenous protein. All of these three combined will represent our protein bypass from the ileum into the caecum, or the large intestine caecum. So here our protein bypass enters our large intestine. Some will pass into the ceca, where it will undergo putrefaction, protein fermentation. Many protein fermentators are pathogenic bacteria in nature. And so protein could serve as a fuel source for pathogenic bacterial proliferation, production of toxic compounds such as indoles and scatols, and can lead to some reductions or some increases in leaky gut, reductions in gastrointestinal health. When I was at the university at Texas A&M, and we wanted to try and produce a model of a natural necrotic enteritis challenge, one thing that we always tried to do was increase our crude protein level and introduce lower digestible ingredients such as well, there's a variety of different ingredients that have lower digestibility values than soy meal, but we would add lower digestible ingredients, increase our crude protein level. And what we were trying to do was increase the amount of bypass protein that was present for Clostridium perfringens to be able to ferment and proliferate and produce toxin. So again, we want to keep that protein level down, can benefit our birds. This is the thing that everybody is concerned about when you introduce protein. This is the impact of reducing crude protein in laying hens. Here you can see protein ranges from 18.5 to 15.5, no difference in egg production. But what we do see is we see increases in daily feed intake as protein level decreases. We see increases in feed efficiency, and we see decreases in egg mass. And so this is the concern, right? Well, if I reduce my crude protein, am I going to lose performance? Well, when you take a look at this paper and you look at the diets, I like to focus your attention to these bottom three that are boxed off. Here you look at arginine, tryptophan, and isoleucine, and as the authors reduced their crude protein while they maintained lysine, methionine, and threonine across the dietary treatments, these lower amino acids, they did not maintain the equivalent concentrations. And in diets 3 and 4, these 3 amino acids are below breeder recommendations. Thus, the reason responsible for the reduction in protein. If we would have utilized synthetic amino acids to increase the digestible ratios of these amino acids, there's a good chance, more likely than not, that those birds would have performed equivalent to the control. So this is what this author here did. So they ran a study reducing crude protein by 2.5%. And then in the reduced crude protein diet, they added back the synthetic amino acids in order to meet the recommendations of either the breeder or to meet back to the control diet. And here you can see is once they added tryptophan, isoleucine, threonine back to the level to get back to the control, you see equivalent performance on egg production, equivalent performance on feed conversion ratio, and similar feed intakes across those two treatments. So you have to maintain the balance of the lower amino acids, and if you do that, you should not observe any sort of performance drop. So here, if you look, we got two different scenarios here. We have red bar and blue bar. A red bar is a diet utilizing methionine, lysine, and threonine, whereas our blue bar is utilizing the methionine, lysine, threonine, and valine. So here on the red bar, you can see we're hitting our minimum recommendation for valine, and we have some fairly high levels or excesses of isoleucine, arginine, and tryp. However, when we utilize valine and the L-valine in the diet, we see that our isoleucine comes down to our requirement. We have just little bit of excess of arginine and tryptophan from what we need from breeder recommendations. So we reduce the excess. We're going to reduce the amount of nitrogen excretion that we have from the diet. So this is a kind of a scenario that you would see as you utilize additional amino acids in your feed. Now, one thing that I want to mention here, one thing about dietary leucine. So leucine in a corn soy diet is going to be elevated. It's going to be over the minimum every time. So when you look at corn and corn distillers and soybean meal, you can see here in corn, we have 3 to 4 times the amount of leucine that we have valine and isoleucine. Recommendation on a broiler is about 110% of lysine, but we're going to have extreme excess if we're using a corn-based diet. Soybean actually extremely balanced when it comes to our branch chain. So as we reduce crude protein level, we have to make sure that we maintain the balance of these amino acids that have potential antagonisms to each other. And the branch chain amino acids absolutely do. And why is that? Well, that's because all 3 branch chain amino acids share the first 2 steps of their catabolic pathway and compete for the same degrading enzyme. So therefore, if isoleucine and valine are at the recommendation or at our nutrient spec, and leucine is in excess, leucine is the most potent stimulator, which increases the catabolism of all 3 amino acids. Thus, excess leucine in the diet, if you're at the requirement for the other 2, could potentially cause a negative response or a marginal deficiency. So we look at some practical finisher diets in the U.S. where we're corn soy with some animal protein, 5% distiller's grain or 10% DDGS. Here you can see with isoleucine and valine, we're at or near the requirement. However, when we're looking at leucine, we are at 147, 152, and up to 158. So we are in extreme excess of the amount of leucine necessary. That additional leucine may potentially cause a problem. So we wanted to, so CJ has spent over the last 2 to 3 years investigating the effect and the proper branch chain balance. And this was the first study that CJ America worked on with the University of Arkansas with Dr. Michael Kidd, trying to determine if, in fact, leucine does have a negative response on performance. And so we evaluated this in a box Binkin design. This is our surface plot curve showing feed conversion ratio. So we have isoleucine and valine on our X and Z axis here. The surface plots or the surface curves inside the 3-dimensional plot represent our 3 leucine levels of 110, which is at the requirement, 130, and 150. And as you can see here, these 3 planes, if we're in the middle of this cube, these 3 planes, which would be at our requirement where we formulate our diets, we see increases as we go from 110 to 110, and then another increase from 110 to 130, and then another increase from 130 to 150. So as we increase leucine in diets at the requirement, we see increases in feed conversion ratio associated with that leucine, indicating that there is a branch chain antagonism present in chickens. Therefore, we wanted to follow up and see, okay, how does this influence our valine requirement, or does it? So we actually ran 2 valine titrations ranging from 60 to 88 in a diet containing 150% leucine and a diet containing 145% leucine. We ran quadratic polynomials to obtain our optimum ratio. The solid line is the low leucine diet, the 115. The dotted line is the 145. And as you can see, when we run our quadratic polynomials, identify our optimum valine ratio. At 115, our optimum valine ratio is 75 to maximize body weight gain. However, at 145, our optimum ratio is at 81. So as we increase leucine, we are shifting the requirement curve higher. Same thing, feed conversion ratio. We see that a feed conversion ratio, to optimize feed conversion ratio at a diet containing 115% leucine, we need 74% valine. However, Increasing that to 145 shifts it over to 79. So as we have more leucine, we need to have more valine in the diet to optimize performance. This is not a new concept. Jackson and Potter in 1984 published a paper where they were in turkey poults showing the impact of body weight gain and feed consumption that added leucine had in the diet. So as they added leucine in a diet containing no L-valine, they saw significant reductions in feed intake and significant reductions in body weight gain. However, those same additions of leucine in a diet containing added L-valine at 0.44%, eliminated the negative response or the negative impact on body weight gain and feed intake. So the increase in L-valine balanced the excess leucine and allowed for equivalent performance. That led us on our most recent adventure to conduct a central composite design in Ross 708 by 344s, and we conducted this in conjunction with Aviagen, trying to identify the response or the proper branch chain amino acid balance. So let me walk you through these graphs real quick. So we have 5 different surface plots at 110, 130, 150, 170, and 190% leucine to lysine. Then we have increasing valine going left to right and increasing isoleucine going from top down. The surface plots are the max response observed. So in this first diet here, you can see the red dot. That's our max body weight gain response for that surface plot. As we move to 130, you see we lose the red dot, which means we weren't able to achieve our max body weight gain. And then as you go from 130 to 150 to 170 to 190, what you see is that yellow circle shifts to the right and down, indicating that as we have more leucine in the feed, as we have more dietary leucine, we have to increase the amount of valine and isoleucine in order to have our optimized performance of our broilers. Similar response on feed conversion ratio. Again, the biggest bullseye that we have here is at 110. We have the most room for error with low leucine in the diet. As we increase leucine, we see our bullseye get smaller and it's shifting to the right and down. So we have to have more isoleucine and more valine in order to maximize or optimize our performance. And this is just a different depiction. Here you can see this is a 3-dimensional graph at 110 and 185 showing the optimal performance. So at 110 to optimize FCR, we need 79 valine and 65 isoleucine. However, when we increase to 185, we need 84 valine and 71 isoleucine. Now, this is a very interesting observation that we saw with total white meat. So if we look at the total amount of breast meat on the bird, again, the blue dot is our maximum response. And as we increase the amount of leucine in our feed, we observe increases in the amount of total white meat weight that we achieved. Now, again, you still have to adjust your valine and your isoleucine appropriately in order to get the optimal response. But leucine, being the stimulator of mTOR, which is which upregulates the production of skeletal muscle, is increasing the amount of breast meat or skeletal muscle that we have on this broiler. So indicating that maybe leucine is not all bad. We can utilize leucine that's in the diet if we properly balance the branch chains to maximize yield, maximize performance. But the balance is extremely important. One other thing that we observed here that was interesting was we removed feathers from the birds at processing. We analyzed the feathers for crude protein content. And we noticed that in the low leucine diets, we had a max protein response or at 96% protein in the feather. However, in the high leucine diets, the max observed crude protein level is 92%. So there's a 4% reduction in the crude protein level of our feather just due to the amount of leucine. Now, remember, the high leucine birds yielded more breast meat weight. They had more breast meat on there. So we believe that the birds are mobilizing nutrients to make, they are preferring to make breast meat over feather condition. Now, for broilers, obviously there's some potential there from a scratching, downgrade potential. But if we think about from a breeder standpoint, if we overfeed our breeders and allow breast muscle accretion on our breeders, what does that have to do, or what potential impact could that have on feather condition, feather quality for our broiler breeder pullets and into our broiler breeder house? So something that was kind of an interesting observation. Now, what we've done is we've taken the surface plots that we've generated from this experiment. We've developed a model that can basically tell you what your optimum branch chain ratio is. And so in this experiment, if we wanted to optimize feed conversion, the model suggests that we use a 110 leucine level, a 79 valine ratio, and a 64 isoleucine ratio. And our optimum response would be a 1,330 grams of body weight gain, a 1.54 feed conversion ratio, and we would obtain 517 grams of breast meat. Now, the U.S. industry, if we put in the U.S. industry averages, which is leucine levels about 150% of lysine, that's a pretty good U.S. average. And if you look at the average U.S. diet, you're probably looking at a 75% valine and a 67% isoleucine ratio. The model suggests that we would lose over 40 grams of body weight gain during that finisher phase. We would lose 4 points of feed conversion ratio. Although with the higher leucine level, we would achieve equivalent levels of breast meat weight. However, if we use the model based on the U.S. level of 150, and we say, okay, we know our leucine level is 150% of lysine, the model would suggest that we should adjust our valine and our isoleucine ratio to 80 and 68. This would allow us to increase our body weight gain by 20 grams, reduce our feed conversion ratio by 2 points, and increase our breast meat weight that we achieve by 5 grams. So that adjustment, just that adjustment in valine and isoleucine will allow us to optimize the performance of our birds. So just to conclude, producing dietary crude protein and using feed-grade amino acids such as L-Isoleucine, valine, arginine, and tryptophan can be extremely beneficial. It can assist producers to reduce nutrient excretion, improve the sustainability of our industry, reduce the environmental impact that we have, improve the environment within the house for the animals, from a reduction in nitrogen output, reduction in ammonia production, reduction in litter moisture, improve our gastrointestinal health, and improve the animal welfare pulse scores as well. It's key to remember that proper amino acid balance is the key to optimizing performance in reduced crude protein diets. We need to maintain the proper balance of amino acids, understand what our lower essential amino acid ratios need to be, maintain a proper branch chain amino acid balance, and really understand what the impact that our ingredient profile can have on the ultimate performance and the impact of those amino acids in the order of limitation. And amino acids are key to optimizing performance and profitability, especially in times now where we have commodity volatilization, extremely high costs for corn, soybean, and other grains. We have seen a significant increase in the last 12 to 18 months within the U.S. market of folks using fourth and even the fifth limiting amino acid right now, as we continue to see this volatilization within the market. But just in addition to saving money on a per ton basis, the changes within the diet will allow for performance improvement, the benefits on gastrointestinal health, the benefits on pulse scores, and the benefits on animal welfare will not only allow you to save money on feed, but also allow you to capitalize on performance benefits and even enhance your profitability even more. I'd like to thank you for your time, and I would look forward to any questions at the end of the meeting.